Looks like they got a little astrophysics in here. That's kind of cool. But funny that like this is the only formula, right? This is kind of an obscure thing. So first off, a parsec is a little bigger than a light year, right? So one parsec is 3.26 light years. So a light year is how far, of course, light travels in a year, right? And a parsec is what's cool is that it's literally we're triangulating to these stars, right? So here's the sun, here's a distant star, right? And we are here, we're orbiting the sun. Some of these things are exaggerated, right? So here we are in January, here we are in June, right? So 6 months later, we're over here, right? Maybe not precisely, I don't know, right? But they pick a time when we're on one side, pick a time on the other side, right? And then what you do is you look at the star, and what you got to know is that behind the star, these distant stars, it might as well just be, they're so far away that this little tiny distance we move doesn't change their perception, right? Okay, it's like if you put your finger out at arm's length, right, and you move your head side to side, the background doesn't shift, but your finger does, right? Close things shift. That's parallax, right? Okay, what they do is they line this star up, and in June it lines up with this star right here, right? And in January it's to the right of this star. And of course, these positions are well known. This angle right here is your parallax angle. Okay, it's the P, I guess, the parallax angle. And then keep in mind that is in arc seconds, right? So 1 degree, of which there are 360 in a circle, right, is 60 minutes, right? So a minute is minute. Okay, sorry. But it's 300,600 seconds. Okay, and parallax, and in these angles, even though a second is really small, right? A parallax angle, a pretty good size one, it might be like 0.04 seconds. They use like the two things like that to mean seconds, right? God help you, the English system. Although the metric, this is metric as well, right? Okay, but we use that for inches, and then a single one for feet. Okay, so whatever they give you, you've got to turn it into arc seconds, right? And then you can plug it into here, and then 1 over that gives you the distance in parsecs, right? And it's just, obviously we should be using tangent or something like that. But these angles are so small that we don't really need to do that. Now, additionally, okay, what's cool is that one of the stars that we have parallax on is the North Star. Parallax isn't like this. It's not that big, right? It's really quite small, right? But the North Star is also a variable star, a type of variable star so variable stars, their brightness, if you look at their brightness, right? They go, it's actually, they never go negative, right? Okay, they just get bright, dark, right? And the Cepheid variable stars, the rate at which they go bright, dark is related to their size, which is related to their brightness. So they're sort of a standard candle. So it's kind of cool. We got sort of this overlapping way of we can do parallax on that. Knowing that, right, we can figure out the magnitude of this star. It's a Cepheid variable star, and we can see those in distant galaxies. So that's kind of cool. One of the things I noticed in the description was that you should know the dynamic that makes stars stable. So basically, in the middle of the core of the star, and then our sun, right, all the fusion is taking place in this little bitty thing called the core, and that's of course causing an enormous explosion, which pushes outward. Thermal energy pushes outward. The rest of the sun, though, gravity is pushing inward on the sun, right? Gravity pushes inward, and these two, the sun is stable because there's as much push inward as there is outward. It doesn't collapse, and it shines on and on, right? Interestingly enough, the sun is opaque. It's made of plasma, right? Plasma conducts electricity. Sunlight does not travel through things that conduct electricity, right? So the photons actually are just sort of mixed in here with protons and neutrons and whatever's in here, right? And they just kind of mingle around. It takes them, on average, about 10,000 years from the core to get to the outside and fly freely through space at the speed of light. What else was I going to say? Anyway, so, and then just, eventually we run out of fuel, right? We run out of boom, and the sun will go through a series of contractions and expansions, right? I think the next phase is that it's going to implode when it runs out of hydrogen fuel. And then when it implodes like that, it's going to basically blow itself up, become a red giant. It'll swallow the Earth, I believe, right? And then, I think our sun will just then dwindle. But large stars, right? They can eventually dwindle down to something about the size of the Earth. And then when they cool down, they supernova and they condense into a neutron star about the size of, like, say, Portland or something like that. And anyway, this is really cool. We used to teach it as our option. And there are videos on the site. Oh, let me recommend this. If you're confused about this section in IB, get the book. We have these in the library. Giancoli Physics. They're a white cover book. Look at, I think it's chapter 33 or something like that. Basically 80% of what I know about astrophysics, I learned just reading this textbook. Okay. I really don't know that much, but a lot of it, and there's some good popular books about it too. Yeah.